Assalamu alaikum. Today on 7th January 2021, I'm starting lecture number 1 for week number 14, and the topics that we will cover in this lecture are the phasor diagrams of synchronous generators, the calculations of equivalent model parameters, and the conditions for parallel operation of synchronous generators. So as we all know that when we studied the equivalent model of a transformer in chapter 2, then right after uh, the equivalent model parameters calculation, we had drawn the phasor diagram of transformer. And for drawing the phasor diagram of a single phase transformer, we used an equation that was previously used to draw the equivalent model. If you still recall, the equation was Vp upon A equals to Vs plus Is into R equivalent plus J time Is into X equivalent. That was the equation we used for drawing the phasor diagram of for single phase transformer. In a similar manner, in an analogous manner, what we are doing here, that we have drawn the equivalent model of the synchronous generator as depicted in figure 5.12, and now we will use the equation of this equivalent model to draw the phasor diagram. And what was the equation here? Equation was V phi equals to V phi equals to EA minus IARA minus J excess IA. That is the output phase voltage V phi is equals to the internally generated voltage EA minus IARA minus J times the synchronous reactance excess into IA. Now if we want to calculate EA as our output, so EA would become V phi plus IARA plus J excess IA. So in the phasor diagram, our final output, our resultant is the internally generated voltage EA. So the equation would be written as EA equals to V phi plus IARA plus J time excess IA. Now using this equation, we will draw the phasor diagram of a synchronous generator. What is a phasor diagram? A phasor diagram is basically the relationship among different voltage drops such as V phi, EA, IRA, XSIA, considering the load that is being connected at the terminals of synchronous generator. So phasor diagram represents that what are the different relationships between various voltages at a particular load. For example, in figure 5.13, they are considering a unity load, that is a resistive load connected at the terminals of the synchronous generator. So if the load is resistive, then the output voltage must be in phase with the load current. So that is the case that the output phase voltage V phi is in phase with the load current IA. You can clearly notice in the figure that this is IA along positive x-axis and V phi is also along positive x-axis. So since the load is resistive, IA and V phi are along the positive x-axis. Now the vector IARA or the drop IARA is just the scalar multiple of vector IA. So it will also be along the positive x-axis. So this is IARA. Now for the final J-axis IA, what we can see, we can say that the same current IA is flowing through a resistance, that is the armature resistance RA, and the same current is flowing through an inductor, that is the synchronous reactance XS. So in this case, the voltage drop across the inductance must be 90 degrees ahead of the voltage drop across the resistance. Therefore, excess IA is being plotted 90 degrees ahead of IARA. That is the angle between IARA and excess IA is 90 degree. Finally, what is EA? It is the resultant vector of the three vectors V phi, IARA and excess IA. So according to the head to tail rule, the resultant vector must be plotted in a way that its tail must coincide with the tail of the last vector, that is GXSIA, and its head must coincide with the last vector, that is GXSIA, and its tail must connect or must be coinciding with the tail of the first vector, that is V phi. So clearly our EA, that is the hypotenuse of this right angle triangle, is the resultant vector of this phasor diagram. So this phasor diagram was drawn for a unity power factor or a resistive load. Now coming to the next phasor diagram, which is being displayed for you in figure 5.14e. Here you can clearly observe that the reference voltage, which is V phi here, is along the positive x-axis, while the load current, and since load is connected at the armature, so the armature current is lagging the output phase voltage. So this confirms that the generator is being loaded with a lagging load, with an inductive load. And due to this inductive load, the load current lags behind the voltage applied at the load. As we all know that in inductors, load voltage leads the current by 90 degree in an ideal inductor. So similarly, uh, an inductive load is connected, so the load current is lagging behind the load voltage V phi. Now again we followed the same equation, that after drawing the V phi, we will draw IARA. Now this vector IARA is nothing but the scalar multiple of the vector IA. So you can clearly observe that the directions of vector IA and vector IARA are 100% same. Both are in the same direction. But if you notice another thing, that the length of IARA is smaller as compared to the length of vector IA. Why is it so? Actually, vector IARA is scalar multiple of vector IA. That is, we draw vector IA array by multiplying the current IA with the corresponding armature resistance RA. Now this RA decides that whether the vector IA array would be bigger than the current IA or it will be smaller than the current IA. In case of synchronous generators, you must remember this thing that armature resistance RA are often negligibly small. So if we multiply IA with a negligibly small resistance, approximately zero resistance, what will happen? A very small uh, voltage drop will occur across RA, that is the IA array vector. So therefore, the length of vector IA array was displayed very short because of RA. Okay. Now again, there is a 90-degree angle between IA RA and J axis IA due to same current flowing in resistor and inductor respectively. And finally again EA is the output or the resultant vector of this phasor diagram. And in this phasor diagram, you can easily conclude that for a lagging load, internally generated voltage, that is EA, must be higher. Now the equation of EA is EA equals to K phi omega, which means that if we want to have a bigger internally generated voltage for a lagging load, then we must provide the generator with a larger field current, because K is constant and generator runs at a constant speed, so we can't change K and omega. So what we can change is the flux, and since flux is proportional to the field current, so to increase the flux we would increase the field current. So in short, for an inductive load, EA would be larger as compared to the capacitive or leading load. So therefore we have to provide more field current for an inductive load. Now coming to the third phasor diagram that is being displayed in figure 5.14b. Here you can clearly notice that the current vector IA is ahead of the output phase voltage V5. Output phase voltage is the reference voltage. It is at positive x-axis, that is the 0 degrees, and IA is approximately at an angle of 60 degrees from V5. So this is IA drawn almost 60 degrees ahead of V5. So again, IA array is a vector exactly parallel to the vector IA, but shorter or smaller in length due to the negligibly small resistance of RA. And then again, there is a 90-degree angle between the drop IA RA and the drop J axis IA. The reason is that the same current is flowing through a resistance array, and then the same current is flowing through an inductance axis. So the voltage drop across the inductor must be 90 degrees ahead of the voltage drop across the resistor. Finally, EA is again the resultant of this phasor diagram, but this time we can easily compare and conclude that EA is much smaller as compared to the EA that was drawn for the inductive load. So that was all about the phasor diagrams. Now coming to the next topic, Power and torque in synchronous generators. At the end of chapter 4, we studied two power flow diagrams. One for the AC generators and the second for the AC motors. So if you compare this diagram that is being displayed for you in figure 5.15, it is exactly the same diagram that was discussed at the end of chapter 4 as the power flow diagram for AC generators. We all know that we must provide AC generators with a mechanical input power. So at the input side, the power is mechanical, tau into omega. Tau is mechanical quantity, omega, that is mechanical speed in radian per second, is a mechanical quantity. So we provided the synchronous generator with the mechanical power along with the field current. Then what happened? First of all, we will detect the loss that is known as stray losses. So what are stray losses? I told you in chapter 4 that these are the human errors. After doing every calculation, we still subtract 1% of the full rated power as a human error. After considering every loss, still we subtract 1% of the full rated power as stray losses. So we provided mechanical energy to the synchronous generator, then we subtracted 1% of the rated load as stray losses. Now the generator started moving. So when the rotor of the generator moves, what happens that it causes a frictional and windage loss between the sliding contacts of the synchronous generator and the air as well. So due to these frictional and windage losses, we subtract the loss frictional and windage loss. So after the subtraction of this loss, that is frictional and windage losses, we lump them as mechanical losses. So after subtraction of the mechanical losses, we will consider the next loss. Now consider that the rotor is rotating and it has a supply, a DC supply, so its magnetic field becomes a rotational magnetic field. And this rotational magnetic field causes eddy and hysteresis loss to occur in the stator of the generator due to relative motion between the rotating rotor's magnetic field and the stationary winding of stator. So eddy and hysteresis losses occur at the stator winding, and we lump them together and name them as core losses. So these are the core losses that we will subtract after the mechanical losses. Now coming to the fact that after these losses, the remaining mechanical power is being converted into electrical power. So that's the reason that here the author has written P converted. That after subtracting the stray losses, the mechanical losses, the eddy and hysteresis losses, the power is being converted into electrical power. But right after the conversion of mechanical power into electrical power, what happens that as we connect the generator with a load, a three-phase current flows in the three windings of stator because stator is three-phase wounded. So due to flow of these currents, I square R losses or copper losses, that are the resistive heating losses due to passage of current, these losses occur in the stator windings. So we have to subtract these losses, and the rest of the electrical power is being available for the load to consume or to perform an active uh, power activity or to perform some task that is being given to the generator. So uh, this is the power flow diagram of synchronous generator, and at the output the power written as root of 3 Vt IL cos of theta. We all know that we can compute three-phase power in two ways. 3 wattmeter method, which uses this formula, that is root 3 into the terminal or line voltage Vt into the line current IL into the power factor cos theta. And if we want to calculate the power using the 3 wattmeter method, so it could also be written as 3 into the output phase voltage V5 and into output current, phase current IE into the power factor cos of theta. So in any case, we can compute the output power of a synchronous generator now. And obviously we all know that the reactive power is magnitude time sine of theta of apparent power. So it will be root 3 Vt IL sine of theta. And if we want to compute the apparent power, so it would be root 3 Vt IL, or it would be 3 V5 IL. So that was all about the power flow diagram. Now the next topic is that they are proving uh, a, a, a formula for the output power and the torque of the AC or synchronous generator. So to prove this thing, they have used the diagram figure 5.16. The purpose of this topic is to prove the formula that P is equals to 3 times V5 EA sine of delta over XS. Now from where this figure has come, this figure is just the phasor diagram of a synchronous generator if we neglect the armature resistance. Okay, so if we neglect the armature resistance, then there would not be IARA in the figure. So if you observe the figure, there is no IARA in it. Now EA is just V5 plus JXSIA. Why? Because they said that since RA is negligibly small and the vector RAIA is a vector of shorter or smaller length, then why don't we just neglect it and then perform another calculation to have some vital conclusion. So neglecting the voltage drop IARA has turned the figure into this shape. And now for this figure, what they did, that they considered two right angle triangles. The first right angle triangle where the hypotenuse is XSIA here, the perpendicular is in front of theta, that is known as AB here, and the base is adjacent to the theta. This is the base of the figure. Now we all know that if the hypotenuse is F, then base is F cos theta. In a similar manner, in this smaller right angle triangle, the hypotenuse is XSIA. So the base is XSIA cos of theta. So using this figure, the author concluded that the base of this smaller right angle triangle is XSIA cos of theta, and the length was almost equal to this length. Okay. Now in the second step of the proof, The author took the bigger right angle triangle whose hypotenuse is this EA and whose perpendicular is the same length that we took as excess IA cos theta and whose base is this bigger length adjacent to the angle delta. So this is the second right angle triangle where our required length is now perpendicular of the figure because delta is the acute angle of this right angle triangle, and in front of delta we have again the same figure that was declared as the same side that was declared as excess IA cos of theta earlier using the smaller right angle triangle. Now for the same length we know that our hypotenuse is now EA and we want to calculate or have another expression for the same length excess IA cos of theta. So in our bigger right angle triangle the hypotenuse is EA and the required side is the perpendicular. So we all know that if hypotenuse is F then the perpendicular is F sine theta. So similarly here the hypotenuse is EA, so the perpendicular is EA sine of acute angle and acute angle is delta, so EA sine of delta. So we proved that the same length, that is this length, sorry, this length, the same length can be written as excess IA cos of theta if we consider the smaller right angle triangle, or the same length can be represented as EA sine of delta if we consider the bigger right angle triangle. So what they did now that they compared the two lengths. They wrote excess IA cos of theta equals to EA sine of delta. That was a missing step, so I am writing it. So what they did, they compared the two lengths because we were knowing that the length is exactly the same. So excess IA cos of theta is equals to EA sine of delta. Then they brought excess towards the right hand side and found a formula for IA cos of theta. So this is basically the formula for IA cos of theta. Whenever we need to use IA cos of theta, we can write EA sine of delta upon excess for it. Now coming to the next page, we all know that three-phase power using 3-watt meter method can be written as power equals to 3 into V5 into IA cos of theta. If we compute real power of the generator using 3-watt meter method, so it would be 3V5 IA cos of theta. And for this cos of theta, this IA cos of theta, the author has replaced IA cos of theta with the proven quantity EA sine of delta upon excess. So hence they got an expression for power in terms of electrical quantities. Okay, so this is the power of a synchronous generator. Now we all know that sine of delta could have a maximum value of 1. So hence the maximum power a synchronous generator can provide is basically known as the static stability limit, and it is 3 times V phi EA upon XS. Now, a question is that whether the synchronous generator achieves this power. So the answer is no. Why? Because delta is known as the torque angle, and synchronous generator typically runs at a torque angle of 15 to 20 degrees. And in very special cases, torque angle is increased till thrice of this value, that is 20 into 3. At most, torque angle could have a value of 60 degree. So obviously this 90-degree angle would never be achieved. It's just a theoretical maximum. Okay. So in the last step, what they did, that we all know that P could be written as tau into omega. So they replaced the P in equation 5.20 with tau omega, and then they brought the omega towards the right hand side and got another formula for the induced torque in a synchronous generator. So these were the two formulas that the author was uh, interested to prove. Now coming to the second last topic of this lecture, that is, how can we measure the performance parameters or the equivalent model parameters of a synchronous generator. So we need to compute three parameters. Number one, the internally generated voltage EA. Number two, the synchronous reactance XS. And number three, the armature resistance RA. So these are the three parameters that we want to calculate. And if you recall that when in transformers we have made the equivalent model, then using the open circuit test and the short circuit test, we computed the parameters of that equivalent model. In a similar way, what will happen here, that we will perform open circuit test to calculate the internally generated voltage EA. Then we will perform the short circuit test to calculate the short circuited current IA. And then using the open circuit test and the short circuit test values, that is EA and IA, we will compute the approximate synchronous reactance XS. And finally, using a DC test, we can compute the armature resistance. And if we have the armature resistance and EA and IA with us, we can also compute the exact value of synchronous reactance. So this is the summary that how we will calculate these parameters. Now we will come to the detail of these calculations. Sorry. Now coming to the open circuit test. What happens in the open circuit test of a synchronous generator? We open circuit the armature winding of the synchronous generator. We set the field current equal to 0. Now at no load, we all know that the output phase voltage V phi and the internally generated voltage EA both are equal. So what happens, that we start gradually increasing the field current, and we plot a graph between the field current and the terminal voltage of the synchronous generator. Now this graph can give us internally generated voltage at a particular field current in any of the point that we will be considering. For example, if we consider the point, if we consider this point, suppose, so this would be the field current, and this would be the terminal voltage. Now from the terminal voltage we can easily compute the internally generated voltage. Why? Because if the connection is star connection, then internally generated voltage is just the terminal voltage divided by root 3. And if the connection is delta connection, then terminal voltage itself is the internally generated voltage. So it's very simple. Now coming to the next task, how we perform or conduct the short circuit test. We short circuit the armature winding to make V phi equals to 0. And then again we set the field current equal to 0. Then we will gradually increase the field current, and we will plot a graph between the field current and the output current, that is IA. So obviously it is the short circuited current, so we can have its value at any particular field current. For example, again, if we take this point, so the field current would be this, and its corresponding short circuited armature current, output current, would be this. Okay, so in short, open circuit test gives us internally generated voltage, short circuit test gives us armature current. Now when we short circuit the armature's winding, so the circuit would become like in figure 5.18e. Here you can see that output is being shorted here. So V phi is equals to 0 because it was having some voltage earlier, but we shorted it. We shorted this winding. So therefore now V phi is equals to 0. Now if we perform a calculation, so it's very easy calculation that if we apply the KVL, so IA would become EA divided by RA plus JXS. So in terms of magnitude, we can say magnitude of IA equals to EA whole divided by magnitude of RA plus JXS. And we all know that in complex numbers, magnitude of RA plus JXS would be RA square plus XS square under the root. So now if we consider equation 5.24, we have EA from the open circuit test. We have the value of IA from the short circuit test. So if we divide EA with IA, so it will give us as RA square plus XS square. That is the synchronous impedance. This is the case that if we divide EA with IA, we will have ZS, that is RA square plus XS square under the root. Now if we have calculated RA using the DC voltage test, then we can put RA there and then we can compute exact XS. Or another way is that since synchronous reactance is much bigger than the armature resistance, or we can say that armature resistance RA is negligibly small, so we consider it as 0. So it would become XS equals to EA upon IA. Why? Because if RA is 0, then it would become root of XS square, which will be XS. That is synchronous reactance. So we can compute the synchronous reactance approximately using this formula. Synchronous reactance equals to open circuited internally generated voltage whole divided by short circuited armature current. So if we want to directly compute the synchronous reactance, we can compute it, but it would be an approximation. but not a bad approximation. It is a good approximation. We will come to know this later on. Okay, now coming to the numerical, where they have explained that how these things will be computed. So example 5.1, a 200 kVA 480 volts 50 Hz Y connected synchronous generator with a rated field current of 5 ampere was tested and the following data were taken. So this is a point number 1, 2 and 3 are the given data. So they told us that they performed the open circuit test and they found that the terminal voltage for a Y connected synchronous generator is 540. So we all know that for Y connection, uh, terminal voltage is equals to root 3 times internally generated voltage. So internally generated voltage would be terminal voltage divided by root 3. So hence from this information we can easily compute the internally generated voltage as equals to 540 divided by root 3. Similarly, in the second point, they had directly given you that the load short circuited load current it is found to be 300 ampere, and we all know that in a Y connection the load current or the armature current is just equal to the phase current. So IL equals to IA and it is equals to 300 ampere. So hence we have uh, EA and we have IA. So then we can compute approximate synchronous reactance just by dividing EA by IA. So here this is EA, as I told you that it would be computed by dividing the terminal voltage by root 3, and again as I told you that IA is just equal to IL, so it would be 300 ampere. And then for approximate calculation we can directly use this, that synchronous reactance XS is equal to EA divided by IA. So EA was 311.8, IA was 300. We divided it and got the approximate answer directly, 1.04. And you can compare it with the actual answer, that there is not much difference between the approximate answer of synchronous reactance and the actual answer of the synchronous reactance. Here the approximate answer is 1.04, which was computed directly dividing the EA with IA, while the exact solution came from first calculating the armature resistance and then putting it into equation 5.25 here to get the exact value of synchronous reactance XS. But we can clearly compare, easily compare, that 1.02 and 1.04 are quite close to each other. There is not much difference between the two values. So we can say that the approximate value of synchronous reactance is almost equal to the exact value of synchronous reactance. That is why a lot of authors don't bother to calculate the negligibly small armature resistance. Still, how they calculated the armature resistance, it is a very interesting thing. The third point is that when a DC voltage of 10 volts applied to the two terminals of the generator, a current of 25 ampere was measured. Actually, this is a DC test to find out the armature resistance. I told you that using the open circuit test, we will find internally generated voltage EA. Using the short circuit test, we will find the load current IL or the armature current IA. But to calculate the armature resistance RA, we will perform a DC test. Now this generator was connected to a Y load. So let me draw a Y load for you. So this is the Y load. I am drawing it. Resistance. Again resistance. Again resistance. Although these are the three-phase windings of synchronous generator, I have not made inductance there. I just made the resistance sign. Can anybody tell me that why I did so? मैंने यहाँ पर वाइंडिंग का सिंबल नहीं बनाया, इंडक्टर का नहीं बनाया, सिर्फ रेजिस्टर का ही बना दिया, जबकि थी तो ये वाइंडिंग। क्या रीजन हो सकती है जी? रीजन ये है कि जब आप डीसी देते हैं ना, तो वाइंडिंग का जो इंडक्टर होता है वो तो शॉर्ट ही हो जाता है। जब वो शॉर्ट हो जाता है वो नजर ही नहीं आता। तो अब ये जो 10 वोल्ट्स गुजर रहा है, आप देखिए 3 आरए मौजूद हैं। पहली रेजिस्टेंस की, पहली वाइंडिंग की रेजिस्टेंस जो RA1 मैंने लिखी है, दूसरी वाइंडिंग की रेजिस्टेंस जिसको मैंने RA2 लिखा है, और तीसरी वाइंडिंग की रेजिस्टेंस जिसको मैंने RA3 लिखा है। तो जब मैंने ये करंट फ्लो करवाया, यानी 10 वोल्ट्स का वोल्टेज सोर्स लगाया, तो 25 करंट फ्लो हुआ, 25 एम्पियर। ठीक है, तो ये कितनी रेजिस्टेंस से गुजरेगा? तीनों से, सिर्फ एक से या दो से? तो आप देखेंगे तो पता चलेगा ये सिंपल RA1 और RA2 से गुजरेगा, क्योंकि RA3 इस फिगर में हैंगिंग है या फ्लोटिंग है जिसे कहते हैं इलेक्ट्रिकल इंजीनियरिंग में, जिसका एक एंड कहीं पर भी कनेक्टेड ना हो उसे हम कहेंगे फ्लोटिंग है, हैंगिंग है। तो यही वजह है कि जब 10 वोल्ट्स का वोल्टेज सोर्स लगाया गया, डीसी टेस्ट किया गया दो टर्मिनल्स पर, तो थर्ड टर्मिनल तो फ्लोटिंग था, लेकिन जो करंट है वो पहले आरे और दूसरे आरे से होता हुआ वापस नेगेटिव पोटेंशियल पर पहुंचा। पॉजिटिव से वो चला कन्वेंशनल करंट, और पहले आरे से गुजरा, दूसरे RA2 से गुजरा, और उसके बाद नेगेटिव पोटेंशियल पर वापस आके टर्मिनेट हो गया। तो आसान अल्फाज में ये 10 वोल्ट्स का करंट दो आरे से गुजरा, इसीलिए V अपॉन आई तो R होता है ओहम्स लॉ के तहत। तो इन्होंने V अपॉन आई को 2R क्यों लिखा? क्योंकि जो रेजिस्टेंस थी वो RA1 और RA2 का सम थी, तो वो 2RA1 थी। तो इस वजह से यहाँ पे उन्होंने, ये बाद लोग ये समझते हैं क्योंकि चैपमैन ने एक्सप्लेनेशन नहीं दी, वो समझते हैं गलती कर गया कि V अपॉन आई को उसने R लिखना था, उसने 2R लिख दिया। गलती नहीं की, चैपमैन बहुत ऑथेंटिक ऑर्डर है, ऑथेंटिक ऑथर है, ऑथेंटिक ऑथर है। उसको पता था कि जब दो टर्मिनल से मैं कनेक्ट करूंगा तो रास्ते में दो आर्मेचर्स रेजिस्टेंस आएंगी, इसीलिए उसने V अपॉन आई को 2RA लिखा। तो V भी दिया हुआ था 10, I भी दिया हुआ था 25, तो 10 अपॉन 25 इक्वल्स टू 2RA, और फिर 2 को इधर भेज दिया, तो 10 अपॉन 25 इंटू 2 इक्वल्स टू RA, तो RA आ गया आपके पास 0.2। और जब RA आ गया 0.2, तो अब एग्जैक्ट कैलकुलेशन के लिए, जैसे मैंने पहले बताया था कि जब RA पता हो तो एग्जैक्ट कैलकुलेशन के लिए फिगर इक्वेशन 5.25 यूज होगी। RA की वैल्यू पुट कर देंगे, EA हमें ओपन सर्किट टेस्ट से पता है, IA हमें शॉर्ट सर्किट टेस्ट से पता है, तो इस तरह से हमें एक्सेस मालूम हो जाएगा। ठीक है जी, तो ये चीज जो है बड़ी इंपॉर्टेंट थी। अब आपने यहाँ पर ये याद रखना है कि आर्टिकल 5.7 तक हम लोगों ने 100% ये चैप्टर कंप्लीट किया है, और उसके बाद हमने सिर्फ एक चीज इस चैप्टर में हम सीखेंगे, और वो है कि ये सिंक्रोनस जनरेटर जब पैरेलल में ऑपरेट होते हैं तो इनकी कंडीशंस क्या होती हैं। ये बताना क्यों जरूरी है? ये बताना इसलिए जरूरी है कि ये बिल्कुल छोटी सी बात थी,
जी स्टूडेंट्स, आपको आवाज आ रही है मेरी?
यस सर, आपकी आवाज आ रही है।
आपको आवाज आ रही है?
यस सर।
जी जरा कंफर्म कर दे, आपको आवाज आ रही है मेरी?
यस सर, आवाज आ रही है
यस
आपकी।
सर।
एक्चुअली लाइट चली गई थी, बस मैं बिल्कुल आखिरी टॉपिक की आखिरी बात सिर्फ आपको दिखानी थी। अब मैं आपको जबानी बता देता हूँ, फिर वो पेज जो है वो दूसरे लेक्चर में दिखा देंगे जब शुरू होगा। लाइट असल में हमारी चली गई, तो बात ये बता रहा था मैं कि सिंक्रोनस जनरेटर्स जो है वो पैरेलल में यूज करने की क्या कंडीशंस हैं। और पहले उससे ही बात ये मैं करना चाह रहा था उस वक्त जब लाइट चली गई एकदम से, कि व्हाई वी यूज सिंक्रोनस जनरेटर्स इन पैरेलल। तो बात ये है कि आप देखें कि अगर हमारा जो नेशनल ग्रिड है उसमें जो इलेक्ट्रिकल पावर आती है और सारी फिर पाकिस्तान में डिस्ट्रीब्यूट होती है, ये कैसे होती है? ये ऐसे होती है कि डिफरेंट प्लांट्स में सिंक्रोनस जनरेटर्स चल रहे हैं। अच्छा, सिर्फ सिंक्रोनस तो नहीं है, कुछ में डीएफआईजीज भी हैं, लेकिन डीएफआईजीज वाले बहुत ही कम है। आप यूं समझ लें कि सिंक्रोनस जनरेटर्स जो है वो ऑलमोस्ट 90-95% ऑफ द प्लांट्स में यही ऑपरेट कर रहे हैं। तो होता क्या है कि अब सपोज हाइड्रो इलेक्ट्रिक पावर प्लांट है तरबेला में, वहां एक सिंक्रोनस जनरेटर है, फिर हमें मंगला का प्लांट चलाना पड़ गया, तो अब उस सिंक्रोनस जनरेटर को इस सिंक्रोनस जनरेटर से पैरेलल में कनेक्ट करेंगे। तो इस वजह से पैरेलल ऑपरेशन ऑफ सिंक्रोनस जनरेटर्स बहुत इंपॉर्टेंट है। तो होता क्या है पैरेलल ऑपरेशन में? पैरेलल ऑपरेशन में ये होता है कि आप जो है नंबर वन, के जो दोनों आपके जनरेटर्स हैं उनके आरएमएस लाइन वोल्टेजेस सेम होने चाहिए, उनके आरएमएस लाइन वोल्टेज एक दूसरे के बराबर होने चाहिए। नंबर टू, के दोनों जो जनरेटर्स हैं जो आपस में पैरेलल कनेक्ट करने आप जा रहे हैं उनका फेज सीक्वेंस भी सेम होना चाहिए। और नंबर थ्री, इसमें ये होता है कि जो दोनों का ए फेज है, पहला फेज है, उनके फेज एंगल भी सेम होने चाहिए। और जो आखिरी कंडीशन है पैरेलल ऑपरेशन की, वो ये है कि जो जनरेटर बाद में आप कनेक्ट कर रहे हैं उस जनरेटर की फ्रीक्वेंसी आपके पहले वाले जनरेटर से रिलेटिवली हाई होनी चाहिए। अच्छा, ये क्यों होता है? ये इसलिए होता है कि जो नया जनरेटर जब सिस्टम में ऐड होता है, ग्रिड में ऐड होता है, तो उसके ऐड होने की वजह से फ्रीक्वेंसी को एक डिच मिलता है, एक डिप मिलता है, वो गिरती है। तो अगर उसकी अपनी फ्रीक्वेंसी ग्रिड की फ्रीक्वेंसी से थोड़ी सी ज्यादा ही होगी, तो एटलीस्ट वो अगर बढ़ाएगा नहीं तो उससे कम भी नहीं करेगा, यानी फ्रीक्वेंसी डिप फिर नहीं होगी। तो ये कंडीशन इसलिए होती है। तो ये चार कंडीशन सिर्फ मैंने आपको लिखी हुई दिखानी थी कि किस पेज पर हैं, ताकि आप वहां से दोबारा रेफरेंस कर लें। तो अब इंशाल्लाह नेक्स्ट लेक्चर में जो है ना वो पेज में आपको दिखा दूंगा। तो यहाँ पर ये लेक्चर कंप्लीट होता है। तो इसमें अगर कोई सवाल पूछना है तो आप पूछ सकते हैं। चले, इसका मतलब आपको समझ आ रही है? चले ठीक है, इंशाल्लाह फिर 10 बजे जो है वो सेकंड लेक्चर स्टार्ट करेंगे। और बाद अगर मैंने बताया था आपको पिछली दफा भी कि इस्लामाबाद में 6-6 घंटे की लाइट जा रही है। तो इन केस के अगर ये लाइट प्रोलॉन्ग कर गई और ये 6 घंटे तक चली गई, तो उस सिचुएशन में जो सेकंड लेक्चर है वो फिर आप लोग कब फ्री हो रहे हैं जरा बताएं बाकी लेक्चर से।
सर आज कॉन्टिन्यूस लेक्चर है तो